but there's a lot more we can do with cat as well. Remember, the name cat comes from concatenate. So we can actually provide more than one file name, and it will print the contents of both of those, or 3 or 4, however many files. It will print all their contents together. So on my desktop, I have quite a few messy files here. I've got one called letters. I'm just going to cat letters. All right, it just contains letters. And then I have this one called words. I'm going to cat words. And there we are. Okay, so I can cat them individually, or I can cat them together just by separating them with a space. And now we end up with one output. Again, not very exciting, but 2 different files were read and then concatenated together in this output, smushed together. So that doesn't seem that useful, but where it gets more exciting, if exciting to stretch, but where it gets more sometimes useful, is that we can then redirect that output to another file. So I could make one file that is a combination of 2 or 3 or 4 other files. So it doesn't have to stop at 4. I just don't want to keep saying numbers. But we can take multiple files, concatenate them together, and take that output and save it into another file. So here's an example of that. I have 3 different shopping lists. One for the butcher. We can just take a look at that. I need ground pork, ground beef, sausage, skirt steak. I've got one for the feed store for my animals. I need to get chicken scratch, chicken feed, oyster shells. I've got one for groceries, milk, eggs, butter, onions, tomatoes. Alright, so I want a master list. So contrived, but I want one list that I can take with me. So I can concatenate all of them. Butcher, feed store, groceries, and then I will take that. First, we can just see what it looks like. Here's the concatenated output. But instead of printing it, let's redirect it into a file. We'll call it everything, if I can spell everything. Okay, now we have a new file called everything. Let's take a look at it. It contains the results of those 3 other files being concatenated. So that can be useful, right? We can take multiple things, stuff them together, and put it in another file. But as we'll see later, we can also actually take multiple things, concatenate them, and send them to other commands, not just send them to a file. So we'll cover that later on when we talk about piping. One last thing with cat I'll mention is that we can use the -n option to get line numbers. So maybe not that useful here. If I go back with that super long Song of Myself poem, if I do cat-n Song of Myself, pretend this is a file with some code and there's a problem in here, I can find that line number and then tell my coworker, hey, it's on 1741. You would probably be in an editor, but we'll also learn about some other commands like find and grep, which allow us to search for things. So we'll get there. There are valid use cases for wanting those line numbers to be available. All right. The next command we'll look at is called less, L-E-S-S. Less is used to read the contents of files. It gives us a nice interactive UI where we can scroll, and it's just a lot easier to work with a file compared to looking at the contents that is printed out from cat. So just as a reminder here, I've got this super long file, Song of Myself. If I use cat, it prints out the entire thing. And I guess that's sometimes useful, but in a super long file, I've got to scroll forever. Yes, I could use head or tail just to get the very top and very bottom of the file, but it's a lot of scrolling. So if I wanted to actually go through this, and I wanted to read the entire poem or look at a massive log file from scratch all the way at the beginning, I could use cat, scroll to the beginning, and now just use the terminal and scroll down. But it's not that easy, it's not a great interface. But if I use less, followed by the file name, so any file name, but a long one, it's ideal because you'll be able to see how useful it is, less songofmyself.txt. Now my screen changes. It didn't just print out the entire text into my terminal window. Instead, it opens up the less program where I see a page, and then I can scroll down with arrow keys, just like the man pages. So if you remember with the man pages, we open up man, some command, our prompt goes away. We're transported to a new world of man pages, and we can scroll. I can hit space to go one page at a time. And there's quite a bit more we can do in less, but first, most importantly, to get out of here, key, just like the man pages. So my history, my terminal is not cluttered with thousands of lines of text. So that's one benefit, but also, of course, I can read things and scroll at my own pace I can also do things like search. So if I want to search in here, my cursor is right here. It's a little hard to see. If I type a / and then I type some phrase or something I'm looking for, I don't know, let's look for green. I don't know if green is in here somewhere, but let's see. I'm going to type green and hit enter, and there we go. This is the first match, the set of green leaves and dry leaves. So that's one thing we can do. By the way, I mentioned you can scroll one page at a time down by hitting the space bar. We can scroll up one page at a time by hitting so B and space. We can also use the arrow keys up and down. We can jump to the end of the file, I believe, by hitting G, capital G. Yeah, we need Shift G. That takes me to the very end of the file. And then lowercase g takes me to the start. So here's the very beginning. Uppercase G takes me to the end. And as always, Q is how I can quit. So this is great to work with long files. It's just easier to navigate. You can search for things. Unlike if you're just looking at the entire file using cats, it's just all vomited on your screen all at once. So that's less. The next command we'll learn is called echo. E-C-H-O. It's very simple. It does one thing. It takes whatever value, whatever argument we pass, and it echoes it back. It just prints it back. It outputs it. So that might not seem useful. Let's get out of here. That's clear. If I just echo hi, well, it just echoes hi back to me. It prints it out. So yeah, it is not that useful when you just run it like that. But one really useful trick is to use echo with a piece of text and then redirect the output to a file. So this is a great, really fast way of making a new file that contains some little bit of text without even having to open up the file. So if I needed to make some config file and it needs to contain, I'm just making this up, but it needs to contain something like, username equals cult, something like that. It needs to have one line in that file. Well, I could make an empty file, I could open it up, and then I could put this in there, save it, close the file, or I can echo it and then redirect to a file that doesn't even exist yet. So that file, let's just call it config we'll just do txt. So it's going to take this argument, it's going to echo it back, but instead of printing it to the terminal, I'm redirecting it to a file that doesn't even exist. It will make that file and put this piece of text in it. So now we have a config file, and if we use cat to look at it, there we are. It contains that line. And I can also, if I needed to add something to it, I can do the same thing where I can append with 2 greater than signs. So if I needed some other config in there, I don't know, how about key equals that. That is now appended into our config file. Take a look. There we are. It has 2 lines of text in it. So this is not how I would recommend editing files, but if you need to make something quickly or just add a small thing to a file quickly, this is a really great way of doing it. Echo some piece of text, redirect it into a file. So to summarize, echo on its own, some piece of text, it echoes it back to you on the terminal, just prints it out. But we can also redirect that. It's a great way to add some text to a file in like 2 seconds. So the next command we'll cover is called WC. It's short for word count. And it does just that. It counts the words in some input. For now, it's going to be a file, but we can actually provide other inputs. And it does more than just word count. It actually will count the bytes and the lines. So if you remember, I have this very long Song of Myself file here. I want to know how many lines are in it. Well, if I run WC and then Song of Myself, it tells me, well, there's 3 different values here. The first one is the number of lines, 1,757 lines. The next one is the number of words. And then third, this little chunk here, that is the number of bytes, and then the name of the file. So if we look at the man page for WC, you'll see that it tells us the order again, how many lines, how many words, and how many bytes. We can also say, actually, I just want the lines, so we can use -L. Or I want the number of characters, -M. Or the number of words, -W. So let's see how many lines. I don't want all that other stuff, but we're going to do WC-L, Song of Myself.txt. There we are. I want to know how many words, -W. Song of Myself, we get 15,767. Okay, so that's one way of using word count. But I'm also introducing a new concept right now, something called piping. So we're directly passing right now a file to WordCount. But with piping, we can do something very different. We can actually take the output of one command and pass it as the input to a second command. So we saw how to take the output of some command like ls and redirect it to some file. This is taking output and then putting it in a file. But what I'm talking about is taking output of a command and passing it to a second command. So what if I wanted to know how many files are in here? So if I do ls-l, this is a massive chunk of text, right? I can take this, and I could, I guess, take it, redirect it to a file, and count the lines in that file. Or I can use piping. So it's called piping because we use the pipe character located above the return key on the right side of my keyboard. I take the first command, ls-l, and then instead of just printing out the outputs, I want to pipe it to the word count command, wc. And take a look at that. You see the number of lines, new line characters, number of words, and the number of bytes. So what we just did was take ls-l. I could even do, let's do al. That will include hidden files if I have it here. There's just 2 of them, but we have 64 lines now. So that's just one quick example. We can also do things like combine 2 different files using cat, and then pipe that to word count. And word count's not the only command we can pipe to. I'm just introducing that one first. I could even do dating. Pipe that to word count. If I wanted to know how many bytes are in there, how many words, it's one line. I don't know if I really want to do that, but we definitely can. But I have a couple of, let's go actually to shopping once again. And I have, if you remember, this butcher file and feed store. But actually, let's do groceries. So I have butcher and groceries. I want to know how many things I have to buy. So I'm going to combine those 2, groceries and butcher, with cat. So cat, groceries, and butcher. And remember, on its own, it just smushes up together and prints it out. But I'm not going to redirect it to a file. I'm going to pipe it to word count. And there we go. If I just want the lines, that will tell me how many items, right? 1 item per line, and it says 9. And that seems correct, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 different things that I have to buy. All right, so that's an intro to typing. It will pop up again and again as I introduce some other commands that are really more useful when you pipe things to them. One more thing I'll show quickly. I can combine piping and redirection. If for some reason I wanted to take this output and then redirect it to a file called number.txt, I can do that. So this will run first, concatenate those 2 files, and then we're taking that information and typing it to the word count command, which is just going to give us the number of lines, in this case 9. And then, instead of printing that out, like we did here, redirect it to a file called number.txt. There it is, number.txt, and if we look inside, well, it just has the number 9. So that's a quick intro to piping. Next up, we'll see some other commands we can pipe to. The next command we'll talk about is sort. So sort does what it sounds like, it sorts information. We'll start by just sorting a text file. So I have this, I'm going to start with our everything file. So let's take a look at that. Okay, so it has a bunch of different items, and I'm going to sort them with sort everything.txt. Now this is not going to change the file itself. This is simply sorting the output. It's going to sort what it gets from this file, it will read it in, sort it, and print out the sort information, but it does not store it in that file. And you'll see we end up with an alphabetical sort by default. So butter, chicken feed, chicken scratched eggs, ground beef, ground pork. It is case sensitive, so a uppercase S comes before a lowercase s. And you can actually tell it to not be case sensitive, I believe. We look at command sort. There's an option in here for where is that ignore case -f. But this is great. This is sorting a file alphabetically, but just generally is not changing that everything file. It is unsorted. Now I could redirect, of course, so I can do this, sort everything, and then put it into a file called sorted everything. And now, if we look at that sorted everything file, it is indeed sorted. We also can tell it to sort numerically. So if I had a file that had numbers in it, okay, I have a file called nums I've just created. Look, nums. It just contains 5 numbers here. If I try and just sort nums as is, it doesn't do a numeric sort. It does, well, it sort of does. It compares, the first digit of each, and at 2. So these both have a 2. That means I guess they come before 54, because that starts with a 5. But it's not an actual numeric sort. But we have the -n option that will now sort things numerically. And there are other sorts that we have at our disposal. We can reverse things with the -r option. So let's do that. -nr. You can see we now have 999 first, all the way down to the number 2. Another option that can be useful has to do with duplicate values. So why don't I echo 999, and I'll append that into my nums file. I'll do that a couple of times. All right? So now, when I recall my source, or nums, there's a bunch of those 999s in there. If I want to only get the unique values, I can use the -u option for unique. So let's do -nu, and now I only get the unique numbers sorted. Alright, so that sorts, we can concatenate and pipe information to sorts. We can do all sorts of things, right? It doesn't have to be from a file, so I'll just show one more example of that. Let's take the butcher file and the, what's another file I have? Groceries. Okay, and if I want to sort those two, I can pipe that. Oops. No, I don't think you can hear my cat there. I can pipe it to sort, and there we are. It sorts what it received as its input. So it wasn't just one file. We took one command, cat, that gets an output, we pipe it over to sort. There we go. I can also do things like, if I wanted to know how many unique numbers are in this numbers file, right? Nums, I could sort nums, but I only want the unique. So -u n sort, oops, not sort, nums. And then imagine there was like hundreds of them instead of, 5. I could pipe that over to it'll word count and ask for how many lines. So take this nums file, only sort the unique values, sort them numerically, but instead of printing the value or the output to the terminal, pipe it over to word count, or we count the number of lines, and the grand total is 5. So this just is to show you that we can take sorts and pipe its output to something. We can redirect its output to a file, or we can take some other command like as and concatenate 2 files and then pipe the output to sort. So that's sort. Next up, talk about the unique uniq command. Now the unique command is generally, at least when I use it, used in conjunction with the sort command. So unique is going to, let's just take a look at the man page first. It reports or omits repeated lines. So anytime you have a data set or a file that contains repeated information on different lines, and you're trying to either consolidate it or ignore repeated lines, we can use the unique command. So just show an example. I have a file here that I just made called Fave Flavors. It was, let's say, we run an ice cream shop. We asked our customers what their favorite flavor of ice cream was. And we got a bunch of different outputs, right? Chocolate, vanilla, strawberry, a bunch of vanillas, Rocky Road, cookies and cream, but there's a lot of duplicated values. Now, if I just run unique on this command, or on this file, fave flavors, well, that's weird. It really doesn't seem like it works because I see a lot of duplicated values. It seems like if it only gives us unique values, or it removes duplicates. We shouldn't see cookies and cream twice. We shouldn't see vanilla twice, or way more than twice. But what it does, it doesn't actually just remove all duplicated values. Instead, it removes adjacent duplicated values. So that might seem weird, right? So we've got strawberry. Let's take a look here. Chocolate, vanilla, strawberry, and then 2 vanillas. Well, if we look at the output from unique, we have chocolate, vanilla, strawberry, 1 vanilla. Down here, we had strawberry 3 times in a row. Over here, it shows up once in a row when we use unique. So it is going to look at one line and the line after it. And if it's the same, then it's only going to print out one of those. So generally, I use this in conjunction with sort. So if I sort fave flavors and then pipe that to, let me just remind you what that looks like. It's alphabetical. So now they're all chunked together, right? Cream, rocky road, strawberry, it's all together. And then I can pipe that to unique. And now we just get the unique values because they were all in a row, and the way that unique works is it's only going to take one anytime there's duplicates in a row. But you might be thinking, see, there's a -u option. And indeed, there is a -u option for sort. Kind of makes this obsolete. But there's additional behavior to the unique command that can make it useful. For example, if I do command unique, there's an option which is -d, which will only print out the duplicates. So I only want the duplicates. Let's try that. Let's do, well, unfortunately they're all going to be duplicates, aren't they? If I do this -d, every single one of these flavors appears more than once. But if I echo about mint into fave flavor, and let's do one more flavor. How about pistachio, or how about rainbow sherbet? Okay, so now we have two values that are not unique. So if I remove that -d, here is all of the sorted unique flavors. So we see a list of them. But with -d, now I only want the ones that are duplicated. So we no longer have rainbow sherbet and mint. Side note, I've always said sherbet my entire life, but I don't know, I've heard it was sherbet. So now I'm self-conscious and I guess I'm sticking with sherbet. So there's another option. Instead of -d, we can use the -u option to display non-duplicate lines. So the lines only appear once. -u. Now we can see, these are the flavors that only one person liked. In our case, we've got mint and rainbow sherbet. Everything else is duplicated, so we don't see it showing up. And then, the fancier option is that we can get a count of how many times each line appears with -c. So I'm going to do that here. I'm going to do sort all the flavors, .txt or fave flavors, and then pipe that to unique. And then -c will give me a count. And we can see, all right, there's 5 chocolates, 6 vanillas, 1 rainbow sherbet. And what's extra fun is that we can actually take the output, instead of just printing it out, I can resort that numerically. If I wanted to get a ranked list, because they all start with a number, I can do dash or sort -n. So sort all the contents of that file alphabetically, which groups them all together. Then take that output and pass it to unique, which is going to weed out all duplicated lines that are adjacent and give us a count for how many times each one appears. But instead of printing that out, pipe that to the sort command again, where we will sort by number at the beginning. And then we can even reverse it with -r, and we can see the most popular flavor, vanilla, so boring, all the way down to the least popular mint, which is, this is not accurate, I think mint is actually so popular. But anyway, that is using piping along with the unique commands. Kind of a lot to take in. So if you just need to sort the unique values in a file, you can do the -u option. But if you want a count of how many times different lines appear, if you want to weed out duplicated values, or you only want an output that contains the values that are duplicated, we can use the unique command. Now, if you remember when I introduced the echo command, if you happen to be somebody watching this entire thing from start to finish, you may recall, at least, when I introduced echo, I talked about expansions and how later on I would cover this thing called expansions. Well, that's what I want to talk about now. What I'm about to show you is not specific to the echo command, but we'll be using the echo command to help illustrate how these expansions work. So when I say expansion, what I mean is that there are special characters and special syntax that we can use with various commands that the shell will interpret and expand to some other value. And probably the simplest example is actually something we've seen before, the tilde. Tilde expansion, if I just echo the character tilde. Tilde has a special meaning. I'll zoom in a little bit. As we've talked about, it is a shortcut that refers to my current user's home directory. So here, tilde is /user/cold steel. Now when we echo it, what we're actually doing is asking the shell print out tilde, but it's not the character tilde, right? If it's in quotes, then we get the tilde printed out. What it's doing instead is it's expanding that character. It has a special meaning. Before it even runs the echo command, it's going to replace that or expand it to be this, and that's where it echoes out. So when we do things like cd tilde, again, the shell steps in and says, oh, I know that. Let me expand that, and it turns it into /user/cold steel, and that is where we cd to. So cd to tilde, it's the same end result. All right, so there's other types of expansion though, including $environment variable expansions. So in our shell, there's a bunch of environment variables available. Some of the more common ones are things like $path in all caps. If I echo that, you'll see that it's been replaced with a very long, yours may be much longer actually than this. It's not too bad. If I run it over here on Ubuntu, I think I have quite a long path here. Nah, not too bad either. So it takes this and it turns it into, or it expands it to the value of that variable. Now, if you don't know much about environment variables, don't worry about it. But here's one more example. User. That's an environment variable for the current username. Okay. Now, a more useful thing is path name expansion. So path name expansion allows me to use special syntax, special characters to match different path names. So we've actually seen this before, we just haven't called it path name expansion. I'm in a directory right now. Well, I'm in my home directory, aren't I? So there's a whole bunch of stuff here, different files, folders. Why don't I do this over on Ubuntu because I have some more files to work with. Okay, so when I type echo, I'm just going to use echo again because it's an easy way to see what the shell is doing for us. So it's just going to print back the expanded version of the star character. So if I wrap the star character in quotes, that's what we actually get echoed back. But if I don't have those quotes and I simply echo star, what I see is a list of every path name in this current folder. So every folder, every file name, like Pokemon.txt, Word.txt, and then different folders like cleanup and copies. I'm just matching everything. So the star means every path here. But I can narrow it down. And I can say star.txt, and we've seen this sort of thing before. Again, this is going to then be replaced with matching paths. So this was replaced with all of that. Now if I do star.txt, it's only going to match something that starts with anything, but ends in exactly .txt. Okay? And so here we are. We see our matches that end with txt. Now echoing them may not be that useful, but I can do things like ls-l star.txt. I want to print out long listing information about all text files in here, and there we go. I only see .txt files and all their information. So we also have another character we can use to match path names, which is the question mark. A question mark will match any single character. So this would match any 3 characters in a row. This would match any 4 characters in a row. So let me show you an example. If I echo, and I'll do anything, so the star matches anything, and then a dot, and then any 2 characters. So this looks weird, but it's saying anything that must then end with a dot, and then exactly 2 characters. I don't care what those characters are, but 2 characters. And we don't really match anything, do we? In this folder, guess we don't have any. Alright, well let's try 3 characters. And now we're just matching all our .txt files and .zip files. It's not that exciting, but just as an example, if I were to touch app.py and app.js and main.js, all right. And then I ran the original version here, which is anything with the dots and then exactly 2 characters. Now we're matching those .js and .py extensions. So I'm echoing them. Again, that's not what we would normally do. We might do something like ls, or we could even do rm. If I want to remove all of those files, this is kind of very dangerous, and I don't know if I would recommend this, but just as an example, I could remove those files that have 2 character extensions. That would be a very bizarre thing to want to do, just all 2 character extensions, but I can. rm star dot question mark. So remove all files in here that end with 2 character extensions, and I have it set up again automatically to ask me, prompt me if I want to. So I will say, yes, I'll remove all of them. Remove and remove. Alright, so that's the basics of path name expansion. Next up, we have some other types of expansion. So we'll start by talking about curly brace expansion. Again, I'll use echo. When the shell enters curly braces, and I provide a comma-separated list of values, so I can do something like, let's just do letters to start. A, B, and C. Okay. If I just echo A, B, and C, it's not going to be very exciting. But if I add something before or after, let's do ABC dot txt. Okay? What this is going to do is create every combination of A followed by txt, or .txt, and then B, and then C. And that's what we get. A.txt, B.txt, and C.txt. So whenever these values are separated by commas, I can make files with them if I wanted to. The shell is going to take this and expand it first. So if I did something like touch, and then how about I did app dot, and then curly braces, JS, HTML, CSS, and PY. If I wanted to do that, I'll run it with echo first so you can see what it would make me. App.js, app.html, app.css, app.py. And then if I wanted to actually create that, I could use touch. And that will make me all those files. So there's a bunch of stuff here. Why don't we narrow it down? Well, only ls things that end in 2 characters. Or how about app dot, and then question mark, question mark, question mark, or how about a star? Alright, so we can see what we created. We can also do numbers and provide ranges. So if I echo 1.99, this is going to be expanded to the numbers between integers between 1 and 99. So I could create a bunch of files. How about day, and then let's do 1 to 365. If I was keeping some sort of journal, I'm not making files right now, I'm just echoing it. But the shell takes this, it expands it into this massive list of different numbers, or rather different names, day 94, day 95, and so on. And then I'm echoing it, but I could just as easily touch or make directory and create 365 different directories in a single one. Now there are other types of expansion. I'm not going to spend time talking about them, but basically the concept of expansion is that the shell intervenes before a command runs, expands some smaller thing, usually it's small, into a larger piece of text, and then passes that to some command. And we can use that to our advantage to craft short commands that result in creating hundreds of files, or deleting a whole bunch of stuff, or just matching a bunch of things by defining a pattern, like we saw. If we want to match, anything that starts with the letter F and then ends in anything else, I'm just echoing it, and this is just echoing the paths that match this pattern to my current directory, but then I delete them all. For some reason I didn't want them to start with an F, I could delete them all. Or I could move them all. I could copy them. There's a whole bunch of things we can do. Next up, we'll cover the diff command, which we can use to find the differences between 2 different files. If you've ever used Git, you probably have seen the git diff command. We will actually see what it relies on behind the scenes to generate a diff. But first, let's make 2 files, or at least 1 file, that is slightly different than another. So I have this ice cream flavor file, Fave Flavors file. I'm going to copy it. So copy Fave Flavors. And I'm going to make another file called Fave Flavors 2.txt. It's not very original. Alright, so now we have 2 of them. And if I compare the 2 with diff, at the moment, they are identical. There's no difference. So let's change something in Fave Flavors 2. let's echo another thing in there. How about, what's another flavor? Let's just do mint again. And I'll append that, not with a single greater than sign, to. I want to append to save flavors to.txt. Okay, so now that exists at the end of that file. Just that one extra addition of mint. And so if I rerun my diff between those two files, this is what it tells me. 24A25 mint. And we could spend a lot of time talking about how this works, but to read this change command here, what it's telling us is that on the first file, line 24, on the second file, line 25 was added. So if we change the direction, if we instead compare fave flavors 2 to fave flavors just on its own, now the output says line 25 on the first file, line 24 on the second file was, I don't know if the D stands for deleted, I believe. So, appended, deleted. We can have multiple diffs too in a file. Just if I quickly change something in, how about in fave flavors 2, so let's open that up. I'm going to change something on line 3. I'm going to do strawberry and cream. All right, I'm going to save that file and close it. Now, if I do my diff between fave flavors and fave flavors 2, you see we get two different diffs, right? Two different things that were changed. On line 3 of both files, it was changed from strawberry to strawberry and cream. And then line 24 of the first file, line 25 of the second file, we added mint. Anyway, this is one way of using diff, but what's probably more common and more useful is to see both files side by side with -y. So that's one option if we pass in -y. Although in this case, way zoomed in, it's kind of disastrous, isn't it? On this screen size, because I've tried to make things readable. But if my font were quite small, you'd see it side by side. And then lastly, we have the -u option, which is what Git uses behind the scenes to display its own diffs. And this just gives us a different output. If we look at man diff again, and we go down to -u, output the num lines of unified context. So it gives us some context around each change. So let's do that again. Instead of -y, -u. What we see here are the files that we're comparing, and then context. Descend from line 1 to 6, we can see what was added or removed. And then same thing here, we can see what was added. So this is maybe familiar if you use Git, and that's the basics of the save command. Next up, we'll talk about the find command. So find helps you find files or folders, matching some file pattern. But there's quite a bit to it, and we could have a 20-minute video at least devoted just to the find command. So I'm going to just try and hit the highlights here. The first thing you should know is that we can find files and folders by a bunch of different criteria. We can find based off of, let's open up the man page, based off of the name of the file, the modification time, the file size, the type, if it's a file or a directory or a symlink. There are probably many others that I'm forgetting at the moment. And I'm just going to the man page here. It's quite long, as you can see. So again, we're just going to hit the some of the highlights here. Okay, so the first thing is if we want to find files or directories, we need to provide a location to look inside of. So find inside of, in this case, dots, meaning the current folder, or find in the desktop, or find in my animals folder. And then we provide some sort of criteria, something to search against. In this case, -name, and then some sort of name that we want to find. So I'm just going to search on my desktop. I have a bunch of files, but find will search recursively. So if I do a find dot and nothing else, just find dot, it is going to find every single file nested somewhere inside my desktop. So there's a lot of stuff going on here. If I scroll, I mean, you can see they're all nested. They're actually on the desktop. They're nested multiple levels deep. We didn't specify any way of narrowing what we're looking for. But now let's find everything that has in its name and then instead of quotes, let's search for anything that has, how about the number 7 in it? Anywhere on my desktop or any folders nested in the desktop or folders nested in those folders and so on. Really? Nothing. Why didn't we find anything? Aren't there at least one file here that has a 7 in its name? And the answer here is that it's looking for an exact match. A file that has, and it's called 7. If I made a file called 7 right here, and I reran it, it would work. We found that file. But what I want to do is find any file on my desktop or nested somewhere on the desktop that has the number 7 in it. So this is where the special wildcard characters of a star, in our case, will come in. A star is just going to refer to anything, and then a 7, and then anything else, optionally before or after. So if I do this, we now get a bunch of matches, a lot of Pokemon that I have for a different video I made, that have a 7 in their name somewhere. But I'm sure there's some non-Pokemon. Here we go. Morning Day 27, nested very deep inside of this folder. Or here's, file 257. So we found files that contain 7 in their name. So if I wanted to find all files of a particular type, like all Python files .py, I would put a star, which again means anything, followed by .py. And it looks like there's just one. Let's try a .js. We've got a couple of JS files nested in my desktop. Now remember, dots is where I'm searching inside of, and that's just my current location. But I could instead say, I want you to search only within the stuff folder, if I can spell it correctly. It's not going to find anything, but maybe I'll find txt files. And there we go, we only find txt files inside of stuff. So we can also find by type. I can find directories or files or symlinks. So why don't I do a find on my desktop once again, and all that I want here are any entries, anything that it finds where type is D or directory. Now I forgot to specify where to search. I'll search in our current directory, and I get a list. These are all directories, there's a lot here, but no files. You notice none of the actual files are present, no .txt or .js or whatever, it's just the directories. If I did type F, I only get the files. As you can see here, these are all, and of course they don't have extensions, so you can't tell, but you have to trust me. They are all files for each Pokemon in this case, or whatever you're seeing printed out. These are all files. There are no directories that have been found. Now there's directories referenced in the path to each file, but that's not the same thing as the actual directories being returned as a result here. So we can combine them too. Maybe I want to find directories only, so I'm going to do dash type is D, and name as, I don't know, how about an uppercase E? We'll see if we find anything that contains an uppercase E, and we do. So only directories, somewhere on the desktop, where in their name they have an uppercase E. So here we go, uppercase E, these are all directories. Now, I can also do a case-insensitive version. If I do I name for insensitive, now I'm finding everything that has an E. It doesn't actually matter if it's uppercase or lowercase. So we see things like right there, there's an E in that directory's name. There's an uppercase E and a lowercase E. Okay. We can also do fancy logical things like use the OR operators of dash OR. So let's give it a shot. Let's find anything that has in its name, so in our current location, dash name, it starts with the letter E. So actually, sure, let's do E. So E and then followed by anything. Now remember, if we put a star there, that means anything can come before the E. But what I want is it must begin with the letter, in this case, uppercase E. So we get a bunch of the E Pokemon, and there's some others, Edgar, Ethel, Elvis, instead of the chickens directory. Now, if I also wanted to say, or name starts with, how about F, star. And now I have fall, fungus, as well as espion and files and directories that start with F or E, uppercase only, because I didn't do my name. So that's just a taste of using the OR operator. There's also a NOT operator. We can do things like search by file size, how many bytes, how many megabytes, greater than something. So for example, to find files that are larger than 100 kilobytes, but smaller than 1 megabyte, we can run this right here. So find where type is file, F, and size is plus 100K, greater than 100K, and size is minus 1M, 1 megabyte. So let's try an example. Let's do find where type is file and size is greater than 100 kilobytes. And there we are. We get a list of files that are greater than 100 kilobytes. If I left that size off, we get way more files. We can also do things around time. So if we want to find files that were edited more than 3 days ago, we would do -m time, which is modified time, plus 3. And then we get to the last little bit that I'm going to mention around find, which is this weird looking thing, -exec. This is an option we can provide where we then specify a command that we want find to run on each found result. So this example is going to find all files in our directory, right? Type is file. And on each one, it is going to cat that file out. It prints its contents. I'm not going to run that because on my desktop I've got a million files that it will print out. But let's talk about this quickly. So -exec is just the option saying, hey, I'm going to give you a command I want you to run with each match. And then here's the command, the entire command we're providing. And we do have to terminate it with this backslash and then a semicolon. That is how the terminal knows where that command ends. And then this, the curly braces, opening and closing, is going to be replaced. It's a placeholder. It will be replaced with each found result. So let's try an example. When we recall this line, where we found files that were larger than 100 kilobytes. Well, we could verify the size of files, one way at least, is with -l, ls-l rather, right? And we can see the file size here. And there's a lot of them. There's a couple that are larger, but most of them are pretty small. -l is going to give us that long listing. So what I want to try is taking these files that we find that are larger than 100 kilobytes, and then telling find to then call ls-l, and then curly braces, and then we need our backslash semicolon. And of course, my font is quite large here, but what you can see is that for each one of those results, if I just run find without -exec, these are the results, right? GG. I think it's great. G.txt, Pokemon exercise, Nano exercise, whatever these different files are, they're all here. But we actually executed ls-l with each one, and we can see that file size is large, much larger than the other ones. We could do something instead, like if we wanted to cat each file out, but again, there's going to be quite a few things printed out. So all files larger than 100 kilobytes, -exec means I want you to then run each match with cat curly braces. Just concatenate them all. Oh my goodness. That's a lot of stuff that is just printed out. A lot of it is kind of messed up, but there we are. That is the result of executing that cat command with every single one of the found files that matched with our find command. Alright, so there's a lot more to find. You can do some really powerful things, but that's just a quick intro. Next up, another command that could have its own video for 20-30 minutes at least, grep. There are many articles, many tutorials that are quite long that exist solely to explain all the different options and various ways of using grep. So what it does is it helps us find text inside of files. So the find command helps us find files, right, based off of their file name or different attributes, but it's not searching in the files. Grep will search inside of files. So the simplest way to use it is to run grep and then tell it some string or some text or something that we're trying to find, and then a file to search inside. So let me show you an example here. Let's clear this screen, all this craziness. I have this Song of Myself file. Here I opened it in Lex. There's a lot of stuff in here. And I want to find every time this file, I don't know, mentions green in it. So I can do grep green songofmyself.txt. And it prints out to me the matches, right? It highlights them in a different color, of every time in this file the word green showed up. So we've got green leaves, green and violets, dusky green, pale green eggs, quintillions green. There we go. We can also ask grep to give us the line numbers. We can -n option, so we'll add that in right there, -n. And now I'm getting the line numbers, so 32 is the first one, all the way to line 1026. I can also ask for some context. If I use an uppercase C, and then I provide an argument, a number of lines I want, in this case 2, that will give me 2 lines before and 2 lines after each match. So let's try that. C, and then 2. And here we go. So this is one match. This is actually the last match on this line. We have 2 lines before and 2 lines after. Here's another match, right? We have 2 lines after, 2 lines before. Another option we can pass to grep is -r, which is for recursive. And this is a bit different. This will actually tell grep, I do grep -r, and then provide some pattern, like chicken. It's going to tell it to search recursively. In my case right now, just in the current directory, in all nested subdirectories. So instead of just looking inside of one file, like, hello.txt, which doesn't exist, now I can look inside of all files. At least if I tell it starting points, I think the default is just dots. Okay, so what we see here is a bunch of matches, one from gg.txt, or a couple from sorted everything, feedstore.txt, website.html, greatgatsby.txt. So these are all files that were nested somewhere in my desktop, and they all contained chicken. Now, it's important to note that it is case sensitive, so if I did uppercase C, no matches, but I can make it case insensitive with -i, now I get my matches again. Now what makes grep really powerful is that it can work with regular expressions, which I'm not going to go over right now. If you know about regular expressions, you know the syntax, you can provide regex patterns to grep to search against. So you can find all matches of an email pattern or a phone number pattern, that sort of thing. Okay, well, I changed my mind. I'm going to show a quick example. I'm not going to explain any of it because regular expressions is its own crazy topic. But what I'm doing here is using a pattern, this is a regex, that will match email addresses. So I'm searching across recursively, across, in my case, the home directory, tilde, for any matches to this email pattern. Alright, so I didn't check this out myself, just to be clear, I found an email regex, but I'm going to run it, and you'll see a bunch of different emails that have been matched. Bing@search.mozilla.org, toolkit.mozilla.org, toolkit@mozilla again, Firefox. These are all coming from some documentation, looks like. Firefox, here's some other ones. Anyway, the point is, we can match these patterns across our file, across our entire machine, and there are tons of powerful regular expressions that you can write, but we're not going to talk about how that works. It's a whole different topic. Anyway, that's a quick intro to grep. Next up, DU, disk utility. I think that's what it stands for. Just let you verify. That would be the logical thing it stands for. Well, disk usage. No, I'm totally wrong. I'm pretty sure it's disk usage. Anyway, what we can do with DU is find the sizes of files and directories on our machine. So if I just run DU in my current directory, wherever I am, it's going to give me an output of all of the other directories in here and their sizes. So you can see, if I just pick one of these, let's find something slightly larger here. Sure. This tar demo folder is 32 kilobytes. This wildlife folder is 16. This cleanup directory is 156 kilobytes, and so on. And then, down at the very bottom, I can see my actual current folder right here is dots. is 136 megabytes. I can provide a folder to look inside of instead of just my current directory. I can say I want to know the Pokemon exercise folder. What's its size? And it's, let's see, 24. Okay. We can tell it to give us a different format, megabytes or gigabytes, using -G for gigs, -M for megabytes. So let's do du, everything here, -M for megabytes. It's all just 1, maybe 2. If I do it on my Mac here, we may get some more stuff. Not a whole lot, but some of this stuff, here's something 410 megabytes. Here's something that's 25. Now, you may notice it's not actually giving me the units, it's just 1 or 0 or 10. If I use -H, which is for human readable, it now is giving me a human readable size. So 4K, 24K, then also for some of these larger things, we get, gigs, 5.7 gigs. So this is what I use most of the time if I actually need to read something as a human, -H. Now, here's kind of a nifty thing we can do. If I want to find the largest storage space on my desktop here, I can do du-h for human readable. Okay. And I can pipe that to the sort command. Now, we're almost there. It is sorting, but the way that it's sorting is not exactly correct. If you notice here, it's doing a sort, once again, based off of the digits. So it's saying, 9.2 M megabytes is somehow smaller than 900 kilobytes. So it's putting all the nines together. That's a start, but it's not actually sorting them. So sort actually gives us an option. If I go to man sort, it gives us an option -H. Oh, where'd you go? I lost it. Here it is. Human numeric sorts. So it sorts by numerical value, but it takes into account prefixes or suffixes like K or M or G. So it's for human readable numbers. So let's run this again. We are going to get a human readable format from du of all the files on my desktop, sort them with -H to make it a human readable sort instead of the default sort. And now, if we go to the top, we get our smallest files, in kilobytes, and down at the bottom, we get our largest files. And if I wanted to find the top 10 largest files, for example, I could then pipe that to tail. That would be one option. And there we go. I'm getting the 10 in this case, because that's default for tail, largest. Or I could reverse with -R and instead get the head, which will be the same thing, right? I'm now getting the sort is in reverse order, and I'm taking the first 10 instead of the last 10. Anyway, that's an intro to the du command. The next command we'll see, nice and quick one, is df. Not to be confused with du. The du command showed us file sizes and folder sizes, whereas the df command will tell us information about the mounted file systems, how much space they take up and how much free space they have left. So I'll just show you very quickly here. If I run df with no arguments or options, I'm going to see some output here. Yours will look different. The file system, so each individual file system, and then the amount of size that it has been allocated, how much it uses, how much is available. Now this by default in Ubuntu is 1 kilobyte box. It's not so easy to read. If I switch over and use the -H option for human readable, now we get megabytes and kilobytes and gigs and that sort of thing. Okay, so